Okay, let's start the class. Today we will finish talk about the RNA transcription and translation, and then next week we'll finish talk about the lactal operon. The next week Thursday we will do a review. Okay, so and over the weekend I will put the review question, the practice question for you to do, and then November the 8th there is no class because general midterm election, and November 10th will be the exam 3. Okay, and I already write on the lab section what we will be tested for you, and we'll talk about in the lab section more detail. So here is something we want to talk about. Go back to here. We already talked about the DNA replication. Okay, then based on the central dogma, it's going to become the RNA transcription. And then we'll move on to is RNA translation. And this is pretty much the outline we mentioned several times. This is called the central dogma. Now here is a very simple question you need to think about. What is called transcription? Transcription is still letters to letters. So basically we know, if we say it very simple, this is the DNA, double strand. Use DNA as a template, let's say ATGC. Okay, TACG. Use DNA as a template, then to synthesize an RNA, and we will mention it is actually mRNA, and then go 5' to 3'. So UAGC. So it is still letters to letter. But how about translation, what that means? Translation, think about what is translation. If I speak Chinese and you speak English, and if you don't understand the Chinese, there are some people have to do the translator. And the same thing here, this is from letters to amino acid sequence. So you need to know the difference between these things. Okay, that's letter to letter, translation, transcription, letters to amino acid sequence. And this is typically has a lots of information there. So this is the first thing we want to mention about before we talk. Okay, so we will focus on is, first of all, we want to talk about is RNA transcription. So that's the first thing we talk. And we already said that using DNA as a template and to synthesize mRNA. Okay, now the first thing first. What is the difference between DNA and RNA? That will be the first question. Ask yourself, what's the difference? First of all, DNA, if we go back to see the structure, okay, base, phosphate, H, OH, this is gone, is that right? So, what is called? That is 2' deoxyribose. Then what is RNA? Very much similar. Most of the structure are very similar. We had a base, HOH, H, CH2, O, phosphate. These are very much similar. What's the difference? That 2', you have this O there. Is that right? So this is 2' ribose. The first difference is deoxyribose versus ribose. That's the first thing. Okay, second thing. How about the base? What is the base, the gene base of DNA? A, T, G, C. How about RNA? A, U, G, C. Instead of you have a thymine, here you have a uracil. That's a major difference. Okay? Number 3. DNA most of the time is double stranded. Most of the time, what I'm talking about. RNA, most of the time, single stranded. Last thing, when DNA we talk about is a replication, there is somehow is proof reading or mismatch repair system. However, during the RNA transcription, there is no such function. If there's a mistake is already there, it's going to be continued. So this is something at the beginning you need to know the major difference between DNA and RNA. Next thing we also want to mention, what are the 3 types of RNA? What are the 3 types of RNA? Right there, along in the slides. mRNA is message RNA. This is carry-on, we call it a codon. And we will talk about later on. 3-letter password. I always say 3 letters password for amino acids. It's a codon. Second thing is tRNA. That's called a transfer RNA. And be very careful, transfer RNA is always carry-on. Anti-codon. Last thing is all RNA. What is that? That's ribosome RNA. Ribosome RNA basically is a ribosome structure. It's a structure. Okay? So this is RNA. You have 3 different types of the RNA. And you can see the slides right here, each describe what happened there. Okay, next one. We want to mention about the transcription. The detail. So RNA transcription. RNA transcription, if we say it very simple. Okay, I'll have the double DNA right here. Double helix C, 3' to 5', 5' to 3'. Somehow, somewhere, there is a small chunk of sequence. Right there. Is called promoter. Will be recognized an enzyme, a big chunk of enzyme. That enzyme is named very well because RNA synthesis, transcription is also become longer and longer the chain. So we also call it a polymerization, and that is called RNA polymerase. And they combine together, they start to do the transcription. And then later on, what they generate is this mRNA sequence. And you always remember the transcription, the function is also always from 5' to 3'. That's very interesting, it's all the same. So, we want to talk about these things one by one. First of all, we want to talk about the initiation. This will be is a key for RNA transcription. Okay. We would love to talk about this enzyme first. So since RNA transcription is also the long chain synthesis, so polymerization, therefore, we want to mention this RNA polymerase. RNA polymerase, first of all, this is a hollow enzyme. Okay, therefore, we could review what we have before. Hollow enzyme composed by core enzyme and coenzyme. Coenzyme basically is a protein structure, is a protein area, and this is a non-protein area. If the coenzyme is strictly, or we say firmly attached, and we call it a prosthetic group. If it's loosely attached, we call it a cofactor. Okay, RNA polymerase, what's the components? RNA polymerase is very interesting, composed by two subunits of alpha 2, beta prime, and omega. This is a coenzyme. So coenzymes, there is 5 subunits because there is a 2 alpha. Then you have a cofactor, which is a sigma factor. The sigma factor will help RNA polymerase to recognize the DNA promoter. And we also mentioned DNA promoter is a very conservative special sequence. Okay, now we want to talk about what is a DNA promoter. Now, by the way, what I'm talking about here is bacteria, is prokaryotes. Okay, what you will say, oh, it is different from what you learned in your biochemistry class because you study eukaryotes, it's different. Okay, DNA promoter, what it looks like. I have 2 double bands, double strand of DNA. 5 prime to 3 prime, complementary with 3 prime to 5 prime. Let's say the initiation of RNA transcription, I'm always label +1. This is the mRNA gonna comes. Okay, that's 5 prime to 3 prime. Goes that way. Everything happens. The gene sequence on the right side is we call downstream. On the left side, by the way, upstream. This is the first thing you need to know. Now it's very interesting. In most of the bacteria, in their normal life, start from the +1 position, upstream, around 10 base pair. There is a special sequencing, rich TA, TAAT. And corresponding to the second band is AT, ATTA. This is called -10. We also gave them a name called pyramidal box. That's the first signal, which is a conservative sequence. Then we, around the jump, 17 to 18 BP base pair. Continue in the upstream, around -35 area. There is another sequencing. TTGACA. That's called a -35. And corresponding to AACTGT. This is -35. The sequencing between -35 and -10, this area is called DNA promoter. This DNA promoter will be recognized by sigma factor. Now, this is a standard, is for the bacteria in a normal life. And people find bacteria in a different life, in a different situation, their sigma factor are different. For this one, it is always sigma 70. And you can see, if in a heat shock response, it is sigma 32. Their sequence is different. When we talk about chemotaxis, motility, flagella, rotation, it's sigma 28. The sequence is also different. Can you see it? So just want to tell you is it is sigma 70 basically is a normal life. I just say it's a normal life for bacteria. That's sigma 70. Okay? So this is the first thing you need to know is at initiation. It's a key. Okay, when we first do the initiation, what's going to happen? Then it's of course the process is we call it elongation. So second step is elongation. Okay. Let me just read it. Elongation. Now what happened to elongation? Let's do a quiz. Okay, I had a 2 strand. This is 5 prime to 3 prime. This is 3 prime to 5 prime. This is the DNA. And the DNA have a 2 strand, which is one of the strand on the top, we call it a template. Template band or template strand. And the bottom one, we always call it's a coding band. Sorry, in the opposite way. The top one is the coding band. And the bottom one is a template band. So let's give an example. I have A, T, G, C, C, G, T, A. Okay, so what's going to be the sequencing of a DNA? Is T, A, G, C, G, C, A, T. And this is you should know. Okay, it's a gene complementary policy and then connected with a hydrogen bond. And this is you know. Okay, what is going to be the RNA sequencing? What will be the mRNA sequencing? Always remember, it's 5 prime go this way to 3 prime. What is the sequence? It should be exactly the same as the coding strand. But the only difference is it's not going to be T, it will be U. Is that right? So very simple. This is A, U, C, G, C, G, U, A. And this is running 5 prime to 3 prime. Now, when they do the elongation process, at this moment, we say this is a RNA and DNA hybrid. So that's elongation. It's very simple. There is a question for you, maybe ask you to do the sequence in the exam. Make sure the tricky thing is the 5 prime to 3 prime. Okay, that's always corresponding to 5 prime to 3 prime, one, because they're running opposite direction, anti-parallel, and mRNA should be the same as the first one. That's why we call it coding band. Okay, that's elongation, that's easy. Now, termination. Termination. What are we going to talk about? Termination. How do we know the transcription is going to be stopped? Okay, let's do it again. We have a sequence right here. Okay, this is a DNA sequence. Double helix C. 3 prime to 5 prime, 5 prime to 3 prime. And usually right here, there is an enzyme, RNA polymerase. Is that right? To recognize the promoter, then you're going to generate it. Is mRNA. That's 5 prime to 3 prime RNA. Okay, how do we know it's terminated? Basically, there is 2 things will happen. Number 1, when they go to the transcription, if they go the area has rich U area, lots of U there, uracil comes out. This will become like a stem loop. It will be stopped. So we call the first signal rich U stem loop signal. What will be the second thing? The second thing is we call rho factor. What happened is, there is when they finished, they all of a sudden has something comes out is TUR. When the TUR comes out, it's going to be attracting a very special factor is a RHO, is a rho factor comes out. When the rho factor attached to the TUR, the transcription will be stopped, and this guy will be released, and also similar has a stem loop there. Okay? So, end up with the termination, there are 2 things, is stem loop and the rho factor, either one of them or both sometimes. So the finishing is pretty straightforward. There is not much we can talk, okay? Now, we want to mention something, it's not on the slides, but you should know about it. When we finish the transcription, there is a different type of the transcription when we talk about. In a bacteria, your sequence is like this. We always have a start code. A start code. Then you have this chunk of the transcript area. It's a coding area, we also call it. Okay, we saw it's a coding area. Then we have a stop code. Then we have a big space between that. Then we do the same thing again. We had a start code, coding area, and we have a stop code, and then we have a space again. Now, of course, later on, we have a trailer there, which means it's almost finished. What is this one called? Polysystronic. However, if it's a fungi, Eastern modes, which means it's UKUs, is different. It's pretty straightforward. Start code, coding area, and a stop code. And then you have a trailer. What is this called? It's called a monosystronic. Okay, just want to mention there is some difference between that. Okay, we finished talking about RNA transcription. The picture right here you can read. Then we're gonna move on to the next big one. Is the new slides are already put on the eCampus this morning. If you didn't have it, you can download it. Then we're gonna talk about translation. Then we have a lot going to talk about. The major thing today, we want to talk about translation. If we have time, we're going to talk about the amino acids. Okay? If no time, we'll be move on to next Tuesday. So we want to talk about that. So it will be a big chunk of the blackboard need to be used to draw and talk about all these big information. So this, I'm going to remove this. So, we move on to RNA translation. Okay, RNA translation. We already said letters to amino acid sequence. Or just say amino acid code. Okay, so first thing first. RNA has A, U, C, G for base. We said every amino acid is 3 letters codon system. Okay, so we will end up with box number 1, box number 2, and box number 3. Can you tell me, theoretically, how many genetic code will be generated if you have 4 gene base and 3 boxes? It is a simple math. How many possibilities in the box number 1? Could be either of them, is that right? A, U, C, G. So 4. How many possibilities are going to be second box? 4 again, is that right? How many are going to be a third box? Is that 4 again? So how many theoretically? 4 multiplied by 4 multiplied by 4 equals 64. Now, how many amino acids we'll care about? Can you tell me? Yeah, 20. I had a joke yesterday, last week. Some people, I said I'd write an amino acid side chain. Then one of the students asked me, how many amino acids? Then I said, you don't know how many amino acids have a side chain? then will be a big problem. Is that right? So how many? If you tell me 20 amino acids, it's okay. If you tell me 21, that's fine, because the new textbook is talk about 21. But if you don't tell me you don't know, that's a big problem. Okay, 20 amino acids is composed by natural, most of the animals, human beings, microorganisms, life bodies is composed by 20 amino acids. So, theoretically, 20 amino acids have a 64 codon. But how come there's only 61? Is that right? You know there's only 61. Why? Because there is a UAA, UGA, and UAG. Those three are stop code. Stop code, we also call it a nonsense code. They are not really translation any of the amino acids. There's only tell you the translation going to be stopped. This is the first thing we want to mention. You have to know. The second thing you also need to know, in their life cell, they are very strict to the position of number 1, to the position number 2. They'll give you flexibility for the position number 3. Which means every amino acids could have 2 to 4 different codes. Genetic codes, they are the same amino acids. And they give more flexibility in the third box. This phenomenon we call it a wobble. Wobbling, obviously. We call it a redundancy, or we call it a degeneracy. Okay? That's called a wobbling. So, give you an example. GGA, GGG, GGC, GGU, they are all for glycine. And the UUU, UUC, they are all for phenylalanine. Now there is something which is only one has, which is AUG, only for MET, is methionine. Okay, let's give you some of the examples. You don't have to know the genetic code. If you need it, we'll give you a table. I just know some of them. Okay, right here. This is what we call a wobble situation. Okay. Now, before we talk about detail of the translation, there are several things you need to know. First of all, amino acid. Because 3 letters, it's a codon system. It's for the amino acid. So what is amino acid? What is the basic structure of the amino acid? Amino base, NH2, C right in the middle, basically it's a chiral C, is that right? Only glycine is a difference. You have H, you have a COOH. This guy, if you really want to write in the chemistry, it's COOH, and the side chain is R. Carboxy group. Carboxy, this is amine group, or amino group. And there is a 20 different amino acids, or 21 different amino acids. Basically, this all side chain are different, is that right? So, if R is H, what is that? Glycine. If R is CH3, what is that? Alanine. If R is, make it a little bit complicated like this guy, what is that? Phenylalanine. And if let's make it more complicated, if it's CH3, sulfide, CH2, CH2, what is this? Methionine. We're going to talk about this later, okay, if I have time. So this is amino acid, is the basics. The first thing you need to know, that's the structure of the amino acids. Now in your biochemistry class, they mention this is maybe like a theta, this is like a phi. It's not really straightforward. It's like a 180 degrees Celsius angle, but depends on the situations. It may go this way, that way. And then they call it a sequential system because it's a positive charge, negative charge, or balanced, or whatever. Blah, blah, that is your biochemistry class. So we don't talk about that detail. But you at least need to know the basic structure of amino acids. Okay? That is what we talk about. Second, when we talk about RNA translation, there is a big chunk of here you need to know, which is tRNA. What is tRNA? First of all, this is called a transfer RNA. Okay, transfer RNA, you always remember their carrier is anti-codon. Is not codon. Okay, this is the key. Lots of people think it's carrier codon, it's not. Then what is the basic structure? It looks like fabulous. It looks like a leafy. It's like this. So lots of people say it's like a clover leaf. Just a leafy shape, okay? 5 prime to 3 prime. Is that correct? 5 prime to 3 prime, okay. What are these names? This is, is where is the anti-codon is. So we call it an anti-codon arm. What is this guy? Variable arm. What is here? T theta C arm. Then you have a PY, PU, all those very weird gene base. Do you remember there is a quiz for sometimes when you're taking general microbiology or biochemistry? They give you a big sequence to tell you A, B, C, D, which one is most possible is tRNA, transfer RNA. How do you know? Because other sequence there is only AUGC or ATGC. This guy has those weird gene base, T, theta, C, PY, PU, all those, is that right? If you end up with that, most likely is tRNA. What is this arm? It's a D arm. Then you go to see here, the D loop, or whatever it is, it's a little bit complicated. This is an area you're going to accept amino acid. Okay, right there, on the 3 prime. So, this is something you need to know. Okay, next one. This is a little bit started to talk about the detail. When we talk about the translation, we need to go back to do the structure. Where is amino acid comes? The amino acid is carried on with tRNA. But the tRNA carry on amino acids is not for free. They need something. They need ATP to hydrolyze 2-phosphate, become AMP. Now sometimes this is GTP, become GMP, sometimes. And also they need some chemical. They need magnesium. And how they connected. This is you need to know, is this structure. tRNA will just write like this. 5 prime, 3 prime. Sometimes there is some very weird base there. Doesn't matter. Okay, something there. This is the tRNA. Where's the amino acids there? We said it's a codon user, right? You're going to have to carry on. So where it is? Then we're going to go back to talk about this base. Okay, let's say you have a T there. It's H, this is H, OH, carbon number 1, carbon number 2. This carbon number 3 has to be careful. O right here. This is the key. So you go here, you have H, CH2, you have O, here you go, P, phosphate, O. What are they connected? Right here. Then they connected here is an amino acid. We have RH and NH2. COH, R1, R2, NH2. This is a high energy bond. That's where this comes from. Okay, this is the first thing you need to know. What's the enzyme we need? Amino acyl synthase. It's a very good name, synthesize. That's what they start to do. Okay, and you also should know, every time when they start to do, the first thing you know is always the first amino acid is always methionine, MET. Then there is some difference. If it's a bacteria, because it's a formyl, MET, tRNA. What it looks like. Methionine, it's very simple. It's an aldehyde group formula. So you go here, CHNH2, they go here, tRNA. CH2, I'm missing one. This one I sometimes always missing because it's a carboxy group, right? Methionine formula. How about fungi? UKU, it's what you learn. It's MET, tRNA. Okay, then you don't have that one. That one's gone. You don't have that one. Okay? That's something we want to mention at the beginning, what it is. Okay. Once we finish all of these things, we'll get ready to talk about is the whole process, how we do it. Okay. Then we want to talk about that. There is two basic knowledge you need to know when we talk about translation. Translation actually is a little bit complicated compared to transcription. Much more complicated because it's a different machinery. So we want to talk about that. It's very interesting. Lots of them talk about chemical structure. If you really study, you will find it's lots of fun there. Okay. So we want to talk about some things first. First of all, RNA translation. This is actually a review. Where is the location? It's a ribosome, is it right? It's a ribosome. Okay, what does a ribosome looks like? Is that like this? A big crown on the top. Small units is 30s. Remember, Vandenberg subunits is not molecular, so it's not end up with really do a plus. Is that right? Or the large one, 50s. What is the overall weight? 70s. Vandenberg subunits. Okay, that is in bacteria. Underneath 30s, there is a 16S RNA, ribosome RNA. Remember? We talk about that. This is the one, lots of people do the research right now called the 16S RNA biotechnology, molecular microbiology. That's what they have because it's a conservative sequence for bacteria. 50S big units, large units. There is a 23S RNA. There is an enzyme called transpeptidase there. It is also going to talk about later. Okay? So first of all, we need to know this. You had mRNA coming. We'll use another color. It's mRNA coming. This is not all the mRNA. Okay, 5 prime to 3 prime. It's not all the mRNA just coming. We're going to do the translation. No. Lots of you know, you already know. You need the AUG as a start code. This you already know. Translation means methionine. You know that. Another thing you also need to know, there is another special sequence for translation, which is you need to have AGG to be recognized by 16S RNA, and this AGG causes SD sequence. It's called Shine the Garno sequence. Once you have these two signals, they can start to do translation. Okay, this is the first thing you need to know. Now, when we talk about translation, we would love to, first of all, students